Alexander Polyakov predicted a transformative breakthrough in quantum theory in 1981. Faced with phenomena ranging from the dynamical behavior of strings to the confinement of quarks within protons, he realized the need for a new mathematical approach. Polyakov developed techniques for dealing with sums over random surfaces. Polyakov's insight into these chaotic surfaces led him to propose a rough and ready formula for calculating averages over such surfaces, later known as a Liouville field. This proposal laid out the new mathematical landscape needed to explain the behavior of theoretical structures such as strings and to develop a rudimentary model of quantum gravity. Despite the profound impact of his work, the full mathematical subtleties of the Liouville field eluded Polyakov. A group of mathematicians has accomplished what many thought was insurmountable. They have meticulously rearranged Polyakov's original formula and shown that the Liouville field does indeed model the phenomena Polyakov had assumed. Vincent Vargas, a mathematician at the French National Center for Scientific Research, along with colleagues Remy Rhodes of Aix-Marseille University, Antti Kupiainen of the University of Helsinki, François David of the French National Center for Scientific Research, and Colin Guillarmou of the University of Paris-Saclay, not only confirmed Polyakov's prediction, but also advanced the mathematical field of probability theory. Their work effectively bridges the abstract realm of mathematics with the complex realities of physics, opening new avenues for understanding quantum fields. This collaborative effort highlights a critical dimension that addresses the nature of quantum fields, which lie at the heart of leading theories in fundamental physics. In contemporary physics, the most successful theories are fundamental components of fields. These fields pervade space and adopt varying values at different locations. In classical physics, a single field can contain all the necessary information about how a force affects objects. For example, the Earth's magnetic field reveals its existence through the changes in direction and strength revealed by a compass needle at every point on the planet. Fields are equally important in quantum physics, but the situation is considerably more complicated because of the inherent randomness of quantum theory. From a quantum perspective, the Earth produces not a single magnetic field, but an infinite spectrum of magnetic fields. Some of these fields resemble the fields observed in classical physics, while others diverge wildly. The challenge is to condense the infinite manifestations of a quantum field into a singular predictive framework, a task undertaken by quantum field theory, QFT. QFTs model how one or more quantum fields, each with infinite variations, behave and interact. Guided by extensive experimental validation, QFTs have become the fundamental language of particle physics. The standard model is essentially a QFT, depicting elementary particles such as electrons as fuzzy excitations, emerging from an infinite collection of electron fields. Physicists are investigating a variety of QFTs. Some, like the standard model, aim to describe real particles in our four-dimensional universe, 3 spatial dimensions plus time. Others search for exotic particles in hypothetical universes ranging from 2-dimensional flatlands to 6-dimensional super-Earths. Derived from an equation in complex analysis developed by French mathematician Joseph Liouville in the 1800s, the Liouville field characterizes a completely random 2-dimensional surface. Imagine a surface where the height of each point is randomly determined, resulting in a chaotic landscape of infinitely high hills and deep valleys. Although such a surface may seem irrelevant from a physics perspective, the randomness often reveals underlying patterns. For example, a bell curve describes the probability of encountering a person of a certain height. Similarly, the irregular shapes of clouds and coastlines follow discernible patterns with consistent relationships between large-scale and small-scale features. Liouville's theory aims to describe patterns within an infinite variety of random, bumpy surfaces. Polyakov realized that this chaotic topography was crucial for modeling strings that follow surfaces as they move. Moreover, Liouville's theory has applications in describing quantum gravity in a 2-dimensional framework. Einstein's theory describes gravity as the curvature of spacetime, but translating this into quantum field theory reveals an infinite number of possible spacetimes, similar to the infinite collection of magnetic fields produced by the Earth. Liouville's theory combines these surfaces into a single framework, allowing physicists to measure the curvature, and hence gravity, at any point on an arbitrary two-dimensional surface. Quantum gravity means random geometry because quantum means random and gravity means geometry, said physicist Wei Sun. Polyakov's initial discovery of random surfaces involved describing the probability of encountering a particular pointed configuration, similar to how the bell curve describes the probability distribution of human heights. However, his formula did not produce practical numerical predictions. Solving a quantum field theory requires first making observational predictions using the field by calculating correlation functions of the field. These functions describe how measurements of the field at one point relate to measurements at another point. For example, computing correlation functions in the photon field explains the fundamental laws of quantum electromagnetism. Polyakov sought to capture the essence of random surfaces, similar to the statistical relationships that describe a cloud or a coastline. He needed to determine correlations between random heights of the Liouville field. Over the years, he experimented with two main methods: the Feynman path integral and bootstrapping. Both approaches had their limitations until recent mathematical work integrated them into a more precise formulation. This breakthrough provided a deeper understanding of random surfaces and their implications for theoretical physics. Accounting for the infinite number of forms that a quantum field can take is a daunting task. In the 1940s, quantum physics pioneer Richard Feynman proposed an approach to overcome this challenge, but it had serious limitations. Consider, for example, the Earth's magnetic field. To use quantum field theory, QFT, to predict a compass reading at a given location, Feynman proposed adding up all possible configurations of the field. He argued that the observed reading would represent the average of these configurations, a process known as the Feynman path integral. While conceptually elegant, the Feynman path integral is only practical for certain quantum fields. It is not mathematically possible in general to add up an infinite number of configurations over an infinite expanse of space. For this reason, the path integral remains a philosophical tool rather than a precise mathematical method. Physicists can use Feynman's path integral to calculate exact correlation functions only for the simplest fields, that is, free fields that do not interact with others or themselves. For more complicated fields, they resort to approximations assuming weak interactions or perturbations. This perturbation theory is sufficient for most fields in the Standard Model, where the forces are relatively weak. However, it failed for Polyakov, who found that the strong self-interaction of the Liouville field rendered standard perturbation methods ineffective and made the correlation functions incomprehensible. In 1984, Polyakov sought an alternative approach and collaborated with Alexander Belevin and Alexander Zamolodchikov to develop the bootstrap method. This technique gradually leads to correlation functions of a field. The process starts with a three-point correlation function that expresses the correlations between measurements at 3 points in the field and information about particle energies. This is the first step of bootstrapping. From this starting function, 4-point, 5-point, and higher point correlation functions are constructed. However, starting with an incorrect 3-point function gives inconsistent results. Although Polyakov and his colleagues successfully applied bootstrapping to simpler QFTs, they were unable to get it to work for the Liouville field. In the 1990s, physicists Harald Dorn, Hans-Jörg Otto, and the Zamolodchikov brothers discovered the correct 3-point correlation function, which leads to the exact solution of the Liouville field contained in the Dawes formula. In the early 2010s, Vargas, Kupiainen, Rhodes, and David aimed to solidify the mathematical foundations of the Liouville field, formalize the Feynman path integral, and demystify the DOZ's formula. Their approach involved reinterpreting the Liouville field using a lighter random object, the Gaussian free field. they were able to perform reasonable statistical calculations by taming the extreme fluctuations of the Liouville field. This led to a precisely defined version of Polyakov's path integral and was an example of Feynman's philosophy finding robust mathematical application. The team then verified that both methods gave the same results by deriving the Dösz's formula from this precisely defined path integral. Vargas combined the bootstrap procedure with verified mathematical objects and solved the mysteries of the Liouville field. Vargas and his collaborators achieved a rare feat, a non-distorting description of a strongly interacting QFT using a concise mathematical formula that makes precise numerical predictions. The challenge now is to extend these probabilistic methods beyond the two-dimensional Liouville theory. Vargas says that their tools are specific to two-dimensional systems and that higher dimensions present much greater challenges. Despite this, Polyakov's key influenced probability theory, allowing mathematicians to confidently use previously dubious physics formulas. Encouraged by the Liouville work, researchers like Sun are using these methods to solve problems involving arbitrary curves. The rigorous nature of the Liouville field could inspire mathematicians to tackle other complex QFTs, potentially leading to new insights into real particles and forces. This coming together of rigorous mathematics and theoretical physics promises to unlock the deeper secrets of reality, underscoring the ongoing collaborative quest to understand the fundamental nature of our universe. Thanks for listening, and take care.